Greetings from the University of Los Andes from Bogotá, Colombia. Maria is a rover more than ready for the 2025 European Rover Challenge.
Robocol is an interdisciplinary student initiative in Universidad de los Andes with the purpose of fostering technical and soft skills of its members in the fields of technology, science, and creative design applied to robotics.
We've developed an educational outreach strategy that focuses on building a robotics ecosystem for Colombia.
It is worth noting our collaborations with public schools with a social objective and collaborations with the Astronomy Associations of Colombia, Colombia's Naval Associations, and the Universidad de los Andes in multiple events that incentivize interest in robotics and space exploration.
We are Robocol, and we are proud to present to you Maria.
The rover team is composed of 4 main subsystems.
The traction team is in charge of the base structure for the rover, including the chassis, wheels, and necessary support structures all around. The arm team is responsible for the robotic arm and its inner workings, making sure it can complete the necessary tasks.
The sensorics and extraction team, responsible for the extraction and advanced analysis of soil samples. And the autonomous navigation system, responsible for the rover's motion, power, communications, and vision.
Since our earliest projects, Robocol has been driven by the mission of pushing the boundaries of what student-led robotics can achieve. We want to participate in ERC to prove to ourselves and the world we are ready to innovate in robotics. Presenting our innovations on a global stage validates our design philosophy and establishes Robocol as a worldwide leader in student-driven robotics.
Secondly, in ERC, we aim to acquire first-hand experience in every facet of the competition.
Finally, every ERC task will help us expand our collective knowledge, and by learning from the competition, we will return with sharper skills, deeper insights, and a deeper commitment to push the limits of robotics. The rockers are composed by 2 legs, joined together by a 3D printed TPU shock absorber, made to absorb impacts the rover may suffer during its operation over uneven terrain. The whole chassis was made of aluminum due to its low density, but will be updated soon to a carbon fiber coating.
The rover has a built-in system to rotate the wheels both in radial and axial directions. With the self-made cycloidal gearboxes, the rover can rotate its wheels in radial direction, and with the self-made planetary gearboxes, the wheels have enough auto torque for climbing slopes of at least 30 degrees. A differential bar was placed to coordinate the rover's movements and support bending moments caused by the weight of the rest of the components.
The navigation team is responsible for developing and optimizing the rover's localization, path planning, and obstacle avoidance systems to ensure accurate and efficient movement during ERC tasks. It features a combination of RTK GPS, IMU, and vision-based sensors to provide real-time positioning and environmental awareness. Additionally, the team integrates sensor fusion algorithms to enhance navigation accuracy, especially in challenging terrains where GPS signals may be unreliable. To achieve reliable navigation, the team implements real-time data processing. Advanced LAMP algorithms are used to generate and update maps dynamically, allowing the rover to adapt to obstacles. The team also focuses on latency optimization by using onboard image and sensor processing in a Jetson Nano to avoid transmission of unnecessary data.
Our Miyako simulation showcases a fully operational rover design. It demonstrates autonomous navigation toward color-based targets, precise forward-backward movement, smooth left and right turns, and stable slope handling. The system also includes an emergency stop function for immediate safety response.
The Aurus prototype is engineered for reliable vertical lift and high-fidelity target recognition. During the development phase, it employs an MDF airframe chosen for its ease of machining, while carbon fiber chassis is finished. Thrust is generated by 4 2700 kV brushless outrunner motors, powered by 11.1 volts, providing instantaneous throttle response. Electrical power is distributed via PDB-XT60 connector. Command and telemetry links are handled by the MC7RB receiver, offering robust 2.4 GHz performance, ultra-low latency, and failsafe protocols. Positioning is provided by the Ready-to-Sky M8N GNSS module, delivering a digital compass data for waypoint navigation. The SV Pro 4K autofocus camera captures ultra imagery with global shutter, maneuvers, and enabling real-time object detection. An emergency detect protocol is integrated. Upon detecting critical battery thresholds, GNSS signal loss, or uplink failure, the system autonomously initiates a controlled descent. This is all powered by a 3-cell LiPo battery.
The first degree of freedom comes from a rail system mounted on the chassis, enabling horizontal translation and expanding the arm's workspace. Provided by the first motor NEMA 23, controlled by the TB6600 and their central microcontroller, the ESP32. The second and third degrees are provided by the shoulder and elbow joints, each driven by a motor with our own gear reduction system. These gearboxes reduce speed and increase torque, while also minimizing backlash, allowing for the stable and controlled joint movements under load. Our robotic arm, powered by the brushless motor Eagle Power LA8303 and stepper DC motors NEMA 23, which comes with 5 degrees of freedom, is designed for versatility and precision in sample collection.
The motors used by this Dove are the brushless Eagle Power with the implementation of the O-Drive S1 in order to achieve a fast response and precision above the extension movement of the arm. The last 2 degrees of freedom are achieved through a differential wrist, which enable complex orientation during sampling. These DOF are provided for NEMA 17 each. This wrist features 2 interchangeable grippers. One is an under constraint rope lead gripper, ideal for fine adaptive grabbing in precision-based tasks. The other is a rigid gripper with stiff fingers designed to provide a firm hold for strength-demanding operations. Together, this configuration ensures the arms can handle a wide range of sampling scenarios with precision and strength.
Once the soil is in its compartment, water flows through a solenoid valve so that it can reach the analysis center so our science team can conduct their tests.
For the extraction mechanism, the drill goes up and down in a screw-based motion in order to retrieve soil samples from the ground.
Once the drill is up, the carousel spins around its own axis so that the soil can be dropped in the corresponding position.
Our scientific exploration mission begins with detailed regional geology using Google Earth and JMars. We map marinary valleys, identifying technologic faults and key landslide patterns, searching for the landing site that maximizes our discovery potential.
In this search for life, our onboard laboratory is crucial. We'll measure water pH to assess habitability, and our UV vis spectrometer will detect biomolecules. We'll search for amino acids using 9-hydrin, Benedict reagent, and quantify total organic matter with the Wycliffe Black method, looking for chemical traces of life past or present.